And I'm really delighted to introduce Rick today. Rick is a lead biostatistician at the Institute for Research on Equity and Community Health, or known as iREACH here at ChristianaCare. He obtained a PhD in biostatistics at the University of Pittsburgh, and prior to coming to ChristianaCare in 2014, he was Director of Statistical Sciences at AstraZeneca Pharmaceuticals. He has a very long list of publications and has helped multiple clinical investigators and residents here at ChristianaCare. And he's also co-author on several book chapters and letters to the editors. So Rick, thank you so much for being our speaker today, and the floor is yours.
Thank you, Claudine. Can you see my presentation now?
Yes.
Today and the next few sessions are topics suggested by investigators. So in the past, most tech talks are chosen by the speaker, where a specific issue or problem is addressed with a specific method. The data are described in the results. Now, Bayesian analysis is not a specific method. It's an approach to really virtually all statistical analyses. So today's going to be a little bit different. And the approach I'm taking is really going very broad, talking about a lot of the issues that faces statisticians in doing statistical modeling, but from a Bayesian perspective. But along the way, I'll also show and mention the issues that are common to both Bayesians and frequentists. I chose to do this topic not because I'm an expert in Bayesian analysis, because I'm not, I'm a beginner, but I at the time was studying a book, Statistical Rethinking by Richard McElreath. I've tried over the years several times to fill in gaps in my education with either books or going to short courses. And this one landed with me because it's filled with examples. And he wasn't, I'll say, evangelical about Bayesian approach. He explained that it's very useful in his work. He is the director of evolutionary anthropology at the Max Planck Institute in Leipzig, Germany. He was born in Germany, educated in the United States, a tenured professor in the United States, and then went back to Germany. But what he's interested in is causal inference, which means typically is comparing a couple of treatments or interventions and seeing what the effect they have on the outcome. He's not really talking about some of the methods that you may associate with causal inference, like propensity scores or G-estimation. But one thing he does embrace are directed acyclic graphs, DAGs, to map out the relationships between variables before doing the analysis. And I will talk about that later. Start with a very simple example, a 2x2 table. Two groups comparing successes and failures on the two groups, 100 in each group, 50 successes in one, 35 in the other. In the language, the statistical programming language there's one command, prop.test. Now there's a lot on slides here, but I'm going to point out what I think is interesting. And with this simple command in frequentist statistics, you right away get a p-value, you get a confidence interval around the difference in percentages to 15%, and it gives you the proportions also. When results are communicated, you say what you observed. You observed a difference of 15%. You report the confidence interval and the p-value. Now, this is my clumsy approach to doing a Bayesian comparison, but it shows the kind of thinking that goes into a Bayesian analysis. And most of the difference between the two are different for the statisticians, especially in setting up the analysis. You start out with saying what the likelihood is, what the distribution is of what you've observed. So you've observed a proportion from group A and group B. And so the likelihood, I'm just saying here in our language, It's binomially distributed. In a Bayesian analysis, you have to say what your assumption is, your prior assumption for the distribution of those probabilities. And here I'm saying I have no idea what it is. It's uniformly distributed. It could be any number between 0 and 1. Those are my prior assumptions. This is my assumed distribution of the parameters. Forget all this messy stuff in the middle. But what this is doing is generating thousands of samples to see which, and in those distributions, it'll show which are more likely given my assumed likelihoods and priors. And so behind this, there's a data set with thousands of samples, and I show the quantiles, the 2.5 percentile and the 97.5 percentile, which I actually graph here. 10,000 tries at it, and you can see that it's more likely around, naturally, 15%. And the interval, the probability interval, is not that different from frequentist statistics. This shows something that's inherent to Bayesian analysis, which is there's an emphasis on distributions. Your assumed distributions and what you get out of it, your answer, your posterior distributions. It also shows when you have a distribution that's not evenly spread in the end, there's more likelihood in the middle. Now, a lot of that is hidden in frequentist statistics. You're given a confidence interval, and in the back of your mind, you might be thinking, oh, the likelihood or the probability is evenly spread, but it really isn't. If you're assuming a normal distribution, there's more probability in the middle of that confidence interval than at the ends. So with the Bayesian analysis, things are more explicit. When you communicate results from a Bayesian analysis, you're talking about the probability itself, like the probability that the true difference is between 1% and 29%. Or if there's some clinically meaningful threshold, like 10%, which I picked arbitrarily, you can go back to the distribution and say 10%, 77% of the distribution is to the right of that. So you can talk about probabilities and any probabilities that you're interested in. There are no p-values, no p-hacking in Bayesian analysis because there are no hypotheses, no null hypotheses, excuse me. So the communication is more straightforward. In Bayesian analysis, you report the probabilities of the difference that you're interested in. Whereas in frequentist analysis, which I do, which we see in reports, you're reporting the probability relative to a null hypothesis, which is the hypothesis of no interest, that there's no difference between the groups. And hopefully in the back of your mind, but you know it's true if you've done this for a while. The definition of a p-value is the probability of observing a result as extreme or more extreme than what you observed, given that the null hypothesis is true. And the 95% confidence interval is it's an interval that will cover the true value of the parameter 95% of the time. Why are there these differences, these starting points? Because statistical analysis is based on probability. The frequentist approach assumes that the true value of the parameter in your target population is a constant. And the Bayesian analysis doesn't. It assumes that the true parameter, or the parameter rather, is a random variable. You can talk about probabilities of random variables. You really can't talk about probabilities of a constant. You can't say you can say the probability of 5 being greater than 7, but it's a very short discussion. So that's the departing point, why the approaches are so different from each other for the statistician. So what have I learned so far? That for the statistician, there's a lot more work in setting up a Bayesian analysis, even in this trivial one, and I'll go through another example here. But there's also more to results, even in frequentist statistics, than just a few numbers, the estimate, the confidence interval, the p-values. There are assumptions behind it, assumed distributions, and sampling distributions. Since the departing point is probability, and this is a presentation for investigators, I have to talk about probability a little bit. Simple probability always starts with rolling 2 dice. Each die has numbers 1 through 6, and so there are 36 possibilities when you roll 2 die. You can get 1 through 6 on the first die, 1 through 6 on the second one. So for example, to roll the number 3, you can get 2 on the first one and 1 on the second, or 1 on the first one and 2 on the second. There are 2 possible ways out of 36. So the probability of rolling a 3 is 2 out of 36. Probability is all about counting. I needed to put this example in some presentation somewhere because it irritates me so much. Let's say you had 3 die, and there are 3 unique numbers on each one. A has 2, 4, and 9. B has 1, 6, and 8. C has 3, 5, and 7. If you roll the dice, A and B, the probability that the number on A is greater than the number on B is 5 nonths. If you roll B and C, the probability that the number that shows up on B is greater than the one on C is 5 nonths. And if you roll C and A, the probability that the number on C is greater than the number on A is 5 nonths. There's no transitive property for probabilities. How can you show that? By counting. Probability is about counting. So in the top, I have A and B together, and you can count out of the 9 possible combinations. 2 is greater than 1, 4 is greater than 1, 9 is greater than 1, 6, and 8. 5 out of the 9, A is bigger than B. When you have B and C together, 6 is greater than 3 and 5, 8 is greater than 3, 5, and 7. B is greater than C 5 nonths of the time. And then the last one, C is greater than A 5 nonths of the time. Have to count to see which is more likely. One more simple probability example. Let's say you had 3 cards. The first card is black on both sides. The second one is black on one side, white on the other, and the third one is white on both sides. You mix up the cards, you look at the top card, black is showing. What is the probability that the other side of the top card is black? Count the possibilities. The first card can show black 2 different ways, the first side or the second side. The second card can show black 1 way, and the third one cannot show black at all. There are 3 ways for a black card to be showing. 2 out of the 3 is the first card. So given that black is showing, the probability is 2/3 that the card is the first and that the other side is black. As the simplest example you can get, this is essentially what Bayesian analysis is doing. It's counting the possibilities given the data and working backwards to see which distribution is most likely. It was named after Bayes' theorem, which is not Bayesian statistics. It's a probability theorem that's always true. In symbols, the vertical bar means given. The probability of A given B times the probability of B always equals the probability of B given A times the probability of A. And in the Venn diagram below, there's 30 units. Let's say 20 of them are yellow, 15 are pink, and 5 are both yellow and pink. The probability of A given B means focus on B in the denominator, 15 in the denominator. The probability of A, given that you have those 15, is these overlap, this 5. So it's 5/15. The probability of pink is there's 15 out of 30. Probability of B given A, there's 20 here in the denominator, 5 of which are also B. So it's 5/20 times the probability of A, which is 20 out of 30. This is always true. How it's used, I never would have thought of to set up a Bayesian analysis. In an analysis, you're trying to estimate some parameter in a target population, theta. So the probability of theta given the data times the probability of the data equals the probability of the data given theta times the probability of theta. And switching them around a little bit, you get up to the very bottom there. The probability of theta, or the posterior, your answer, distribution of the theta, which you're interested in, is equal to your prior assumptions of the distribution of theta times the likelihood of the data. And I showed you some of these priors and likelihood assumptions in the simple example. We'll do another example, simple linear regression, reminding you that in linear regression, what you're trying to do is predict y given x, and for every x, there is could be a distribution, and what's on that line, the estimated line, is the expected value of y given x. Here, for example, speed being 10, the expected value of the distance given speed is 10 is around 15. This messy stuff is how it would get set up at Bayesian analysis. Height is a function of weight. There's a little data set here that I'll show what it looks like to the statistician. So you start out with saying, how is height distributed? And all of these are assumptions. You start out by saying height is normally distributed, some mean, some standard deviation. That's called the likelihood. Then you have your linear model. The mean height for anybody is an intercept plus a slope times the weight. Now here he's subtracted the average weight. And you'll see several examples here. He, being the author, Richard McElreath, often standardizes variables. Apparently, his justification is you don't have to do it, but when you standardize the variables, it's easier to pick the prior assumptions of the variables. So you'll see that often he does standardize variables by subtracting the mean or subtracting the mean and dividing by the standard deviation. In Bayesian analysis, you need to give the assumed prior distribution for every parameter that you're working with. Here you have alpha, beta, and sigma. The assumption is alpha is normally distributed, beta is normally distributed, and sigma is uniformly distributed. Sigma cannot be negative, so you have to pick some distribution that is non-negative. Where do these assumptions come from? This is why I'm afraid to do a Bayesian analysis myself, is because I would have trouble picking the distributions. So we kind of have to take some of the assumptions that he has as given. But one thing that he does say you need to do is test out your assumptions. That is, literally generate numbers from your assumed prior distributions. And I have an example here of one of these. Beta is assumed to be normally distributed 0 with a standard deviation, mean 0, standard deviation of 10. You should check the priors for reasonableness. So he generates it, and he generates line from those assumed prior distributions, and the lines are all over the place, which is an indication that it's not a very good assumption. in his approach to Bayesian analysis, he tries to not have completely non-informative prior assumptions. He tries to have skeptical prior assumptions that allow for a wide range of answers so that the data have a chance to have the most influence, but he doesn't allow for everything. So the second thing that he gives us is assuming that the slope is log normally distributed. And by doing that, it's a wide range of possibilities with a height of 0, height of an embryo, or the height of 272 centimeters, the world's tallest man. Wide range. But the idea here is you have to check prior assumptions for reasonableness. This is the work for the statistician. Here I have it set up. Even people that are familiar with R will not recognize some of this code because it's code from his rethinking package. So he developed a package, and some of these functions are from his package, so they're not functions that other people would use, even if they use R all the time. This replicates what I showed on an earlier slide. The likelihood is that the height is normally distributed with a mean and a standard deviation. The mean is a straight line with an intercept and a slope, and it's a function of weight. A is normally distributed, the intercept is normally distributed, the slope is log normally distributed, and sigma is uniformly distributed. This just translates into the code. The output from this routine is it's a data set with thousands of generated A's, B's, and sigmas, generated parameters. And from these, you can draw straight lines from A and B, and that's what I've done on the left-hand side. So the estimates just don't pop out as a number. They're distributions, and you have to look at the distributions to get your answer. And this is the estimate of the straight line. It's a pretty narrow confidence interval or a probability interval. I didn't use sigma to generate this curve. If you use sigma, then what you're doing is showing the variability around estimates, or predictions for future observations. And if I use sigma, I get a much wider probability interval. This is not a Bayesian thing. It's true in frequentist statistics too. Your estimate of a line will have a confidence interval that's relatively narrow. But if you're trying to predict future observations out of your sample, the confidence interval will be much wider. So what have I learned? That for the statistician, there is more work to set up a Bayesian analysis. You need to specify or the assumed distribution of the data, which is called the likelihood. You need to specify what your regression model is, which you've got to do for frequentist statistics too. Same thing. And you need to specify and test out your prior assumptions for all of the parameters that are in your analysis. I don't want to leave the impression that everything is different for a Bayesian statistician. The issues in developing a statistical model are the same for both a Bayesian and a frequentist. And I'm going to breeze through some of these because I just want to name these issues to make the point that there's a lot of overlap between the two approaches. Things are not completely different when you go into the Bayesian world. And the one thing is, if you're going to do a study, you have to start with a clear study objective. This is a small data set, a real data set from UC Berkeley, 6 departments, male and female applicants to the department, acceptances and rejections The question is there gender bias in acceptances? We'll start out with a simple model. This is a logistic regression looking for gender with this data set. So the likelihood is that the admission probability is simply binomially distributed. In logistic regression, the transformation of the probability, called the logit, the log odds, is just a function of gender. And a point here, maybe for statisticians, is that when he has categorical variables, he always uses indexes. It's easier to read off the answers, and he said it's easier to specify prior assumptions when you use indices. And the results of the probability will be normally distributed. Running this analysis, the admission acceptance rate for males, the probability of admission given that it's a man, is about 14% higher than for a woman. Let's graph the departments to see how well this predicts the admission rate. It's not a well-labeled graph, but what this is the men and women applicants for each of the 6 departments. In Department A, this is the raw data. The admission rate for men is lower than that for women. For B, it's lower for men than women. C, it's higher for men than women. D, it's lower a little bit. E, it's higher. And for F, it's lower. What these dots are in the middle are what we're estimating from the model. We asked the model to give an overall estimate of the admission rates for men and women. The admission rate for men is higher than that for women. The predictions are horrible because we didn't take department into account. Instead of asking for an overall estimate of the difference in admission rates, what's the average difference in the probability of admission of men versus women within department? Logistic regression, but we now have a variable for gender and also for department. The answer is entirely different. Now, women have a slightly higher probability of admission. That's what the -2 is down here, 0.02. Why? Because women apply to departments with lower acceptance rates. So Department A and B, the acceptance rates are the highest, but the female applications are the lowest. Women apply to departments with lower acceptance rates. The marginal estimate, the overall estimate, is different from the conditional estimate, where you have it by department. Sometimes this is called Simpson's paradox. It's not really a paradox. It's just asking the question differently. So you got to ask the question the right way if you want to get the right answer. The other thing I wanted to note here about what you're trying to estimate, the estimate, is that I'm reporting results here as probability of being admitted, proportions. I did a logistic regression. If it was left up to me, I probably would have reported the odds ratios. But as investigators, it's the choice of how you want to report the summary statistics. And if reporting is probabilities or proportions is more relevant to the question, to the study, than odds ratios, ask the statistician to give probabilities instead of odds ratios. Second common issue to Bayesians and statisticians is very simple. If you just put a variable in a model, the model assumes that the relationship to the outcome is linear. It's not always linear. Sometimes it's not. The statistician needs to check it out. Another issue common to statistician from whatever side they're coming from is multilinearity. When 2 variables are measuring very similar things or the same thing. For a lot of models, prediction models or covariates that you're not interested in so much in the causal model, it's not that big of an issue usually. But if it's correlated with the treatment effect that you're really interested in, it could be a very big issue. The reason is, if you have two variables that are important, let's say treatment is important. If you look at each one individually, you see this is important, this one's important. But if you put them both in the model, they start fighting with each other, and they'll show up to be important, but not as important as they truly are. So you do have to check for collinearity, especially with your treatment variable or your intervention. Post-treatment bias. The cleanest analysis is when you use only baseline variables as covariates. If you have a variable or something that occurs after treatment, there could be a bias. You have to be very, very careful. In a few minutes, I'll talk about a mediator, which is when the treatment affects the variable after and could interfere with your analysis, depending on what you want to estimate. But you've got to be very careful for variables that occur after baseline. Confounding. This is the typical issue that you deal with. So the example that McElreath gives in his book is, does Waffle House cause divorce? The data here are data by states. It's the average divorce rate in state and the average number of Waffle Houses per state. And there seems to be a relationship between the average number of Waffle Houses per state, per million, and the divorce rate. Now, in fact, we know that's not true. It's not a causal relationship. It's partially because there are more Waffle Houses in the South, and the divorce rate is higher in the South. The marriage rate is higher in the South. People get married younger in the South. We'll take this data set to do a simple example. And here you can see that as the age of marriage increases, the divorce rate decreases. That's the graph on the left. But as the marriage rate, the average marriage rate in the state increases, the divorce rate increases. The axes here are standardized variables. I mentioned that he often standardizes variables, but that's why it's not the raw data. We want to investigate this these simple variables here. But another detail before I do this. Something that McElreath recommends and statisticians and epidemiologists interested in causal inference recommend is mapping the causal relationships between variables before you start your analysis. So it's a conceptual map of what you know or think you know about the relation of the variables and the relationships between them. And it's not always going to be true, but it's a starting point for your statistical modeling. And I'm trying to do this more often now because it's a way to help me, the statistician, understand the variables that the physician wants to include in the data set. Because I'm not a clinician and I don't understand the variables very well. So it helps me understand things. So what are the relationships that can occur between variables? One is a fork. So let's say that this diagram in the upper right is the true relationship between X, the treatment, and Y, the outcome. There is no direct relationship if this little diagram is true, but there is a common cause, a confounder called Z. So if I had a data set with X, Y, and Z, and this diagram were true, and I did a little regression analysis, I would find that there is an association between X and Y. And that's what these symbols mean, that Y is not independent of X. However, if I adjust for Z in the regression analysis, then X and Y will be independent. So this is saying X and Y are independent given Z, controlling for Z or conditioning on Z. So this is why you want to adjust for a confounder in a regression analysis. Another relationship which I mentioned is a mediator. All of the effect, according to this diagram, of X, the treatment on Y, is through Z. So if I had data with X, Y, and Z, I would find an association between X and Y. But again, if I control for Z, if I adjust for Z, if I stratify for Z, the relationship between X and Y will disappear. And the last one is a collider, where X, I'll say, causes Z, Y causes Z, or associated with Z. In this case, Z is blocking the relationship. So if I had a data set, there'd be no relationship between X and Y. However, if I were to adjust or stratify by Z, I would create a relationship that isn't there. This slide, I have a little diagram of relationships between the state, the average age of marriage, the marriage rate, the divorce rate, and Waffle Houses. And it's really just to point out for statisticians that if you have a diagram, there's this lovely package in R called DAGity, which will tell you what the minimal set of variables are that you need to adjust for, which the minimal set of confounders that require adjustment. And here, adjusting for A&M will work, or just adjusting for state. So the diagram is a starting point for a model. I'll start with a very simple thing, age, the marriage rate, and the divorce rate. And let's say this is the DAG, where the marriage rate could be causing the divorce rate. That's what I want to test. Age could be a confounder because there's errors going from A. A is a common cause of both the marriage rate and the divorce rate. How do I test it? Simple regression. This is a regression. In the background, it is actually a Bayesian analysis, but it could be a frequentist analysis where I regress the divorce rate over age, just age by itself, and I see a negative slope, which is this graph on the left. If I regress the divorce rate against the marriage rate, I get a positive slope, which is the graph on the right. But if I put them both in the model, the slope for the marriage goes down close to zero. The slope for age is still very negative, which is saying that there's really no direct relationship between the marriage rate and the outcome, the divorce rate. It's all age. So that this is probably the more correct diagram of the relationships. This is a difficult topic. It deserves a special tech talk. Overfitting. What is overfitting? There's 7 data points here. The more variables you put into an analysis, a regression analysis, the better your fit will be usually. So you can put enough variables in your analysis so that you can draw a line through every point in your data set. The upper left is probably underfitting. The lower right is probably overfitting. What's wrong with overfitting? Well, the goal of research is to do research, to have a result that can be generalized to your target population. If you overfit the data that you have, your result will not be generalizable. And detecting overfitting is difficult. So years ago, there was a Japanese statistician going to work on his commuter train, thinking about statistics coming from information theory, entropy and divergence, which measures the prediction error from the data to the true parameters. Now, there's plenty of statistics measuring observed minus expected from your data set. What you really are interested in is the prediction against the true parameters from your target population. Problem is the true parameters aren't known. But he thought that if you penalized by subtracting the number of parameters in your model, you get a very good statistic. So AIC, I can pronounce his name, Akaike. So Professor Akaike came up with the AIC, Akaike information criteria, as a way to measure prediction error against the true parameter. The problem is you don't know the true parameter. So by itself, the AIC number for a regression analysis is useless. But when you compare two statistical models from the same family and you subtract the AIC measurements, the bits of the formula that depend on the true parameter subtract out. And relatively, you can see how important a variable is when you add it to the model on the prediction rate and the prediction error. And since the original AIC, there have been other developments, WAIC, PSAIC. CV stands for cross-validation, which is a procedure with your data set that helps avoid overfitting. Regularization refers to some of what I described earlier by McElreath, where he's trying to get a prior assumption that is not wide open, not informative, but it's skeptical, but not so narrow that it drives the results, but it keeps them in hand. So the issue is to avoid overfitting and avoid throwing everything into the model. And just because you get a better prediction within your data set doesn't mean you're going to get a model that's a better prediction for outside of your data set, for your target population. A difficult topic. And the last common issue for Bayesians and frequentists is interactions. Just to comment that the diagram, the DAG, does not show interactions. And the example that he gives here is the relationship between ruggedness of terrain and gross domestic product by continent, where there seems to be an interaction for Africa, where the GDP is actually better the more rugged the terrain, versus other continents where the GDP is worse for more rugged terrain. And he doesn't dig deeply into this data set, but he suggests that it could be because of the history and slavery that the more rugged domain protected some areas. But if you set up a model with an interaction, and again, for interaction in his, it looks a little different than it does for frequentist statistics and R, where you have, well, it's set up differently. Here is using indices to allow different intercepts and slopes for the different continents. And he gets different intercepts and slopes for Africa, which is a 1, and other continents, which is a 2. So we use indices instead of dummy variables. But it's set up the same way, where you specify the likelihood for your outcome. Here it's log GDP, the linear model, your prior assumptions. And it gets 2 answers for Africa versus non-African nations. And as an aside, he does mention it's better, unless you have a good reason not to do one model where you have information on the variability from all the data, rather than just doing separate models for Africa and non-African continents when you have an interaction. The plots were extracted from posterior parameter distributions. So what have I learned at this point? Although it's a little harder for statisticians working from a Bayesian framework, a lot of the hard work, I'll say most of the hard work of developing a statistical model faces issues that are identical for a Bayesian and a frequentist. And using the tools, whether it's Bayesian or frequentist, correctly is more important than the approach that we take. So why Bayes? These are topics from an article written by an FDA statistician. And I left the pharmaceutical industry 10 years ago. And at that time, it was used heavily in the device industry. Drugs and devices both need development programs to approve a device or a drug. And in devices, they were used in Bayesian analysis because often very minor changes in a device will be made, and it doesn't make sense to do a whole development program to show that the minor changes have no effect on either the safety or efficacy. So they use prior data, which is how they use Bayesian analysis. So the device change could be a cosmetic change. It's often used in early drug development where a lot of the risk is to the sponsor, not to the FDA. Setting up adaptive clinical trials that react to data as it's accumulated is a little easier to set up for this statistically for a Bayesian analysis than a frequentist analysis, although the logistics of doing adaptive clinical trials is very difficult. It's easier to set up non-inferiority studies from a Bayesian framework. Pediatric studies are a challenge. The FDA wants sponsors to do pediatric studies, but development programs always start with studying thousands of adults, and they have to bribe sponsors to do pediatric studies. But borrowing information from adult studies and your prior assumptions is one way to look at pediatric data. There are very, very rare diseases where you want to use the information from the adult program. And then subgroup assessment. If you just look at each subgroup separately, you can get pretty wild positive or negative results per subgroup. By reining in the prior assumptions, you can shrink the estimates for your subgroups. So considering the frequentist analysis, it's simpler to think of the unknown target population parameter as a constant. The computations are easier. Priors are not needed for the computation. But the problem is that the null hypothesis is boring. It does not address clinical significance, which it doesn't talk about the probability of what you're interested in, the physician's interested in, directly. The true definitions of p-values and confidence are such that they're often misinterpreted. And going back to the very first example of a 2x2 table, there's actually no agreed analysis in frequentist statistics for analyzing a 2x2 table. There's a lot of options. Considering a Bayesian analysis, it's a natural way to use prior information. The exact inferences conditional on the data are given. It makes the most use of the data as possible given your assumptions. The results are interpreted. Communication is much better. The choice of the prior requires some skill and knowledge. Experts may disagree when you have published results on the chosen prior distribution. It's more difficult to set up the analysis. And frequentists cannot believe there's no penalty for multiple comparisons. There's no protection against data dredging. Why isn't it used more often? History. 100 years ago, Dr. Fisher, Professor Sir Ronald Fisher, was one of the giants in statistics, and he chose the frequentist path instead of the Bayesian path. path. And since then, a lot of software has been developed for frequentist statistics, not as much. In fact, a lot of the software needed both the numerical methods for complicated analysis to be developed, where the Metropolis algorithm was published in 1953, and further developed Monte Carlo, Markov chain Monte Carlo method, Gibbs sampling, Hamiltonian algorithm were developed more recently, and the computer hardware needed to catch up to the algorithms. So here's Stanislaw Ulam, who was one of the originators back then. I think he developed the MCMC, standing with the Maniac computer back in 1953, which was finally a big enough computer to run the Metropolis. And he didn't develop it for Bayesian statistics. These were nuclear physicists who were developing for physical states. So that's the origin of some of these algorithms. Finally, the end. Should I use Bayesian analysis when I grow up? I'm still studying that book, still working through the examples. And I am intrigued by it. That is, if I had enough confidence to do a Bayesian analysis for some of the projects I work on, I would do it just to see if the tools that it provides lead to any different answers or data checking that frequentist diagnostics don't show up. But there would still be that issue of publishing results. And the reality is, for a lot of the journals that we publish in, that the frequentist approach is expected and probably easier for reviewers to review. That is the end. Are there any questions or discussions?
Wow, Rick, this was great. I love the null hypothesis is boring. I agree. Null hypothesis is boring. Any questions?
There's one in the chat box, Claudine.
Oh, okay. Sorry. Let me check the chat box.
I can
All
answer.
right. From June Chog, would you like to ask your question, or do you want me to read it?
Oh yeah,
Okay, go ahead.
Yeah, thank you so much, Doctor, for this wonderful presentation. And yeah, so I had a very fortunate experience in both analyzing, like, within the academic and also in the industry setting. And, like, when using data science algorithms, it is very common to use cross-validation, like tenfold cross-validation, because we have a lot of data. But then I'm kind of wondering, is that approach is kind of controlling overfitting using cross-validation even practical in an academic setting where there is, like, very few data compared to what we call big data? Kind of wondering what your response is.
I understand your question. So what cross-validation is you mentioned the typical approach. It divides the data set into 10 chunks, and it takes 9/10 to predict the 10th. Then it takes the next 9/10 to predict the other 10th.
Yes.
It leaves out 1/10 at a time and kind of averages the results. And of course, the answer to your question is, unfortunately, no. If you've only got a few hundred in your data set, you can use a smaller number than 10, you can use 5. But some of those other measures that I mentioned, WAIC and PSIS, I had to write down, yeah, I did. PSIS stands for Pareto Smoothed Importance Sampling. It purports to give a statistic which estimates it estimates a number that is, it gives you the same results, I don't know how to say this, that you would have got by cross-validation, PSIS. So it's a way of doing it without actually doing the cross-validation. So for most data sets, the measures that WAIC and the PSIS give very, very similar results. Some of the examples in the book that I was working through. And they show when the addition of a parameter is useful or not, or how good the model is. But you're correct. If you have a small data set, you are left with using those numbers, AIC, WAIC, PSIS, instead of actually doing the cross validation.
I see. Then the follow-up question is, would you recommend using WAIC and PSIS even when we have a lot of data, as opposed to cross-validation? Like, would there be any?
Yes.
Okay.
I'm sort of echoing what the author said, where he relied heavily on these two measures. And he actually prefers the PSIS one because it gives you an error message if there are some issues in the data, and it kind of leads you to dig deeper into your data. So the answer is yes.
Okay. Yeah. Thank you so much.
All right, I have a question.
Of
So,
course.
well, I have several questions. So I know I was really surprised, in fact, what you said at the end regarding null hypothesis is boring, which I totally agree, and about the adjustments for multiple comparisons. So Bonferroni adjustment doesn't exist in Bayesian analysis. Is it what you are saying?
Yes, yes, that's what I'm saying, because there are many ways to adjust for multiple comparisons. All of them adjust the p-value, but in Bayesian analysis, there are no p-values because there are no null hypotheses. So p-values are probabilities that are defined from your observed data relative to a null hypothesis of no difference between the two treatments. But there's no null hypothesis. And so there are no p-values, there's no adjustment for p-values, there's no adjustment for multiple comparison. And this is something that I don't know enough about how it's dealt with, because it seems to me that there's still an issue. And I don't know how the FDA deals with this. There's still an issue, for data dredging. That is looking at a lot of subgroups, taking each subset analysis by itself, other than the regularization that I mentioned in dealing with the prior distributions. And I should have mentioned that there are counterparts to that in frequentist statistics also. So for subset analysis or for variable selection where you don't want to overfit, there are penalized regression analyses, ridge regression, lasso regression in frequentist statistics. So there are approaches in frequentist statistics to try to accomplish the same thing that you can get with Bayesian analysis, working with the prior assumptions.
That's amazing. This is really a different world, because any time we publish and there are multiple comparisons, the reviewer would immediately say, and they should, how did you adjust for multiple comparisons? So it's I think it's super interesting, and that's not something that we've seen a lot in the literature still. And also the issue with subgroups, I mean, very often, we are asked also whenever we write a grant or a paper in a clinical trial, how are you going to deal with subgroups? And you have to define your subgroups first. So I guess in Bayesian, you're still supposed to define your subgroups, right? Before you do your analysis, and then you can put some type of information about whether whether subgroups have some difference or something like that, right?
Yeah, I know what you're saying, and I'm trying to wear a Bayesian hat today, but I don't know everything that a really more knowledgeable Bayesian statistician would say, but I believe a Bayesian statistician would say that it's the data that matters. You're estimating probabilities based on the data. So there would be less of an emphasis on a priori predefining your subgroups. That
I
is,
see.
I believe that they would say that it's fair game to explore the data. The data don't know what your protocol says. So your job is to analyze the data as thoroughly as possible and just take it where the data leads you.
Oh, that's fascinating. It's
It's a
really all
different-
kinds of concepts that are falling, falling down, right?
Well, I don't know,
That's really
falling down. Like I
fascinating.
said, I wish I knew more about how the FDA deals with some of these issues, because the FDA needs to be and has been very rigorous in their statistics, because they make decisions that affect thousands and millions of people on what they approve or disapprove or what's in drugs labels. So if they were to approve a drug based on a Bayesian analysis, I don't know how they would deal with comparisons. I just simply don't know.
All right. Well, Rick, when you know more, can you come back and tell us?
No way. This is the end.
All right. Well, thank you so much. Thank you so much for everyone to attend this this presentation. I think we've learned a lot. And